Welcome to the Flock. Let's dive into writing and balancing half reactions in electrochemistry, just like this one here. Stick around to see how it's done. The whole purpose for writing half reactions is to be able to extract a certain voltage value for us to be able to calculate cell potential later on. So this is a crucial step in order for us to determine how much voltage a chemical reaction can actually provide us. As we already know, in redox reactions, there's always going to be a reduction half or a reduction part where there's a gain of electrons, and there's always going to be an oxidation half. In other words, there's going to be a loss of electrons. Wherever you lose electrons, they have to go somewhere, they have to be gained by another chemical. In order to determine which chemical gains or loses electrons, we need to write in something called the oxidation state, or the oxidation number. Any atom that's by itself or in its standard state receives an oxidation number of 0, as sodium would in this case. And chlorine, a diatomic molecule, is going to also receive a 0 oxidation state, as does any other diatomic molecule. If we look at the product side, we see that we have an ionic compound with a metal bonded to a nonmetal. That's what makes it ionic. When we look to our periodic table, we see that sodium has a +1 charge and chlorine has a -1 charge. We could also perform a reverse drop and swap, where we know that there's an invisible 1 down here, and the 1 would go here, while the other one would go there, with the cation always written first, and the anion written second. Now as we compare our reactant to product side, we see that the sodium went from 0 to +1, and the chlorine went from 0 to -1. In order to become more negatively charged, you must have gained something that was intrinsically negative. In other words, the chlorine must have gained an electron. While the sodium became more positive, that means it must have lost something that was intrinsically negative. So it must have lost an electron, since electrons are intrinsically negative. If you recall from our mnemonic way back in the day, we had oil Rig. Now Rig stands for reduction is gaining. So wherever the electron was gained, we had reduction. And oil stands for oxidation is losing. So anywhere we lose an electron is where oxidation is occurring. Now that means for this chemical reaction, we would only focus on chlorine for the reduction half and sodium for the oxidation half. So what does that look like then? We're going to follow the format of always beginning with our reduction half. I find it easier to think about in terms of where electrons are being added to. In this case, the reduction half is always going to be the one gaining electrons, so that one will end up with electrons on the reactant side. So we'll write Cl2 in its standard 0 state on the reactant side, plus some number of electrons that we don't know yet. There has to be some gain of electrons to that chlorine molecule in order for this to happen. So let's just leave a space for the number of electrons that belong there, and we'll fill that in a second. So we know that that one molecule of chlorine needs to react with a certain number of electrons in order to become chlorine -1 on the product side. Well, then you might say this is pretty straightforward, right? If we had to go from something with 0 charge to something with -1 charge, all we needed to do was add 1 electron, right? Yes and no. There's not just one chlorine molecule over here. Remember, we had diatomic chlorine on the reactant side. That's Cl bonded to itself. So that means that we actually need 2 chlorine atoms on the product side in order to account for the fact that there was diatomic chlorine on the reactant side. And since that's the case, we now have 2 things that have -1 charge. So it's not just 1 electron over here that was added, it was actually 2. Now let's move on to our oxidation half of this reaction. We're only going to be focusing on sodium and what's happening to sodium and its electrons for the oxidation half. So here we see we have sodium on the reactant side with 0 standard state. I'm going to align the arrows here side by side so that it's easier for us to tell which side the electrons are on. I recommend you do the same. We know that in the oxidation half of this reaction, we are losing electrons. So we're going to have to leave a space for some number of electrons lost on the product side. We also see on the product side that we have sodium +1. So we need to account for that down here. Now, in order for sodium to go from a 0 charge to a +1 charge, all we needed was 1 electron to be lost. In this case, there's no diatomic sodium, it's a metal. So it's actually going to have a myriad of other sodium atoms to make the sodium metal in the first place. So notice that we didn't need to account for the fact that there were 2 sodiums here. We're only thinking about the number of atoms connected to make an intramolecular bond and make sure that those atoms are balanced from reactant to product side. So don't worry about the molar coefficients for now. The next problem we encounter when we compare our two half reactions is that our electrons don't balance. That's physically impossible. However many electrons are lost have to be the number of electrons that are gained. Remember the law of conservation of mass. You can't create matter or make matter disappear out of nowhere. So we have to make sure that our electrons are balanced. Since there's 2 in the reduction half, electrons that is, and there's only 1 electron in our oxidation half, if we multiply the entire equation by 2, that should fix our problem. Now the 2 will multiply in to all of the other things present as well. So we'll end up with 2 sodiums, 2 electrons, and 2 sodium +1s. Now we can see that our 2 electrons do cancel out from reactant to product side, and we can write our final overall equation. We're just going to drag down all the other atoms that didn't get canceled. We have Cl2, standard state, plus 2Na, standard state, reacting to form 2 Cl -1s and 2 Na +1s. Now this final overall reaction gives us a more clear picture of what's happening overall with the transfer of electrons, how many there are, and how much voltage can be created from the reaction between sodium and chlorine. But that'll be in a later video. Writing out the half reactions and the overall reaction for this chemical equation proves to be a rather difficult challenge for many chemistry students. See if you can pause the video here and apply the principles you just learned from the previous example to solve it yourself before I give you the answer on this one. Go ahead and give this challenge a try now. Think you got it right? Let's check your answer. Just as we did before, we want to assign our oxidation state values first. We know that iron, by itself, is going to receive 0. Oxygen, a diatomic, will also receive 0. When we do reverse drop and swap from this guy over here, we see +3 would be the charge on iron, and -2 would be the charge on oxygen. Now we see by comparing the oxygen reactant to the oxygen product that it became more negative. That means it must have gained electrons. And if it gained electrons, that must mean it's the reduction half, the Rig part, since it gained. While the iron went from a 0 oxidation state to +3. That means it must have lost electrons. In other words, it is the oil part of the mnemonic, and it's the oxidation half because it lost electrons. As always, let's start with the reduction half because that's the easier one to start with, in my humble opinion. So if we're starting with the reduction half, we only care about what's happening to oxygen. In this case, we start with oxygen, diatomic, in its standard state, reacting with some number of electrons to form oxygen -2. Now, just as before, you might say, oh, this is easy. We went from 0 to -2. That just means we needed 2 electrons. Wrong. Remember, we have oxygen diatomic. There are 2 oxygen atoms connected to each other in one molecule of oxygen. We need to account for the fact that there are 2 atoms of oxygen in this one molecule, so we have to put a 2 here. So really what we have is 2 -2 oxygen atoms. That gives us a total of -4 charge. So what we actually need here is 4 electrons for this to occur. All right, so then what about the oxidation half of this reaction? We're only going to think about iron for the oxidation half and what's happening to iron. We're going to start with iron on the reactant side in its standard state, 0. Line up that arrow with each other, leave a space for a certain number of electrons that were lost because oxidation is losing after all. And account for this +3 iron over here, Fe +3. This one's a little more straightforward in that we don't have a diatomic or anything like that. So it's just 0 charge going to +3 charge. How many electrons did we have to lose for that to happen? Well, 3 of course. Now let's work on balancing our electrons. Down here, if we multiply this entire equation by 4, and up here, if we multiply this entire equation by 3, we can see that the 3 will distribute in to all of these spaces, and we'll end up with 3 O2, 12 electrons, and 6 O-2. If we distribute the 4 in, we end up with 4 Fe standard state, 12 electrons, and 4 Fe plus 3. Now we can easily see that our electrons cancel, 12 electrons gone from both sides because whatever we lost we had to gain somewhere. And now we can write out our overall equation. We have 3 O2 diatomic in its standard state plus 4 Fe in its standard state creates 6 O-2s and 4 Fe plus 3s. One last thing that you should note about the reduction half and oxidation half of these electrochemical reactions or redox reactions is that we also have something called a reducing agent or an oxidizing agent. The oxidizing agent in this scenario would actually be the reduction half chemical. So the oxygen itself is the oxidizing agent, while the oxidation's half chemical, the iron itself, is going to be the reducing agent. You can remember the oxidizing agent as the one that wants to or has the ability to acquire electrons. In this case, the oxygen is the one that has the ability to acquire electrons and become more negative, while the iron, the reducing agent, is something that likes to give away or lose electrons. Typically, those are ones that start with a neutral charge or are negatively charged to begin with, because then they can give away the extra negative electron charge. All right, now that you've seen a couple of these done, go ahead and pause the video and see if you can separate this redox reaction into its half reactions and figure out the overall reaction. Ready? Go! Let's check your answer. If you wrote the charges above each of the chemical species respectively, you would have seen that copper went from a +2 charge to a 0 charge, so it must have gained electrons to go from something more positive to 0, and aluminum went from a 0 charge to a +3 charge, which means it must have lost electrons to become more positive. Now you may have noticed that there was this hydroxide as well. The hydroxide had a -1 charge in both scenarios. It did not change its charge. Therefore, it's what we call a spectator ion, and we don't include it in the reduction half or the oxidation half because it didn't change charge, so it didn't have anything to do with the oxidation or the reduction. In other words, we're just going to forget that hydroxide even exists in this case. We don't care about it at all. Keeping that in mind, you should have found that the reduction half involved copper and the oxidation half involved the aluminum. In order to balance the electrons, we had to multiply by 3, and that 3 would get multiplied throughout to give us 3 Cu plus 2 plus 6 electrons to 3 copper at standard state. Whereas the oxidation half had 2 multiplied throughout, and that would give us 2 aluminum in standard state and 6 electrons plus 2 aluminums plus 3. We see that our 6 electrons cancel to give us the overall equation of 3 Cu plus 2 aluminums, with our reaction arrow going to 3 coppers and 2 aluminum at +3 charge. Hopefully that's the answer you got. Ready to try another one? Here's the last practice for this lesson. Go ahead and pause the video here and see if you can split this redox reaction into its half reactions. Ready? Go! Let's check your answer. Now that should have been your final overall reaction. Again, in this case, the reduction half, the chlorine here, would be the oxidizing agent, while the iodine in this case would be the reducing agent. Now if we wanted to actually make one of these batteries or a galvanic cell using these half reactions, first we want to know what that model would even look like. So let's take this chemical reaction for example. It's the same exact thing that we looked at previously, except instead of hydroxide ion here, we have sulfate. Notice that regardless, the sulfate also doesn't change charge. Therefore, it's again noted as a spectator ion, and we don't care about its existence. And so we pretend that it doesn't exist to begin with, and it has no impact on our actual half reactions, but it will impact what our galvanic cell looks like. So let's try and draw this out. For a galvanic cell, we're going to need two separate beakers. We know that the copper is the reduction half of this reaction. So we actually need a piece of copper metal in this beaker, whereas the aluminum half of this reaction was the oxidation part. And so we also need a piece of aluminum in this container. In order for the electrons to go from one metal to the other, we need a wire to connect the two of them. We also need something called a salt bridge in order for our cations and anions to move from one vessel to the other. We'll need to submerge these metals along with filling the salt bridge with some of the solution that's going to be in these beakers. Now, what's the solution, you might ask? We'd have to go back to our original chemical equation where that sulfate anion was coming into play. So in the copper vessel, we would have copper sulfate, and in the aluminum vessel, we'll end up with aluminum sulfate. According to our mnemonic, an ox ate a red cat, we know that oxidation is the anode. So over here at the aluminum, we know that that would have to be the anode, and we know that the copper would have to be the cathode. This means that as the reaction proceeds, the electrons are always going to flow from anode to cathode. That's where the electrons want to go. So here we can draw the electrons literally traveling along the wire in the direction of the cathode from the anode. When that happens, the copper is going to become more and more negatively charged as it accumulates more and more electrons. This means that the copper is also gaining mass as the reaction proceeds. And as it becomes more positive, the more and more the sulfite anions within the solution are going to be attracted to this positive anode. This also means that the sulfate anions from the other side, the cathode side, are going to be attracted to the very positive side. Therefore, they're going to flow through this salt bridge all the way over into the anode side beaker. Because of this, there are now a lot of these sulfite anions floating around in solution. This causes all of these positively charged aluminum cations to now be attracted to the sulfate anions within the solution. This means that literally the aluminum gets pulled off of the metal into the solution, causing the aluminum electrode to lose mass as the reaction proceeds. Meanwhile, the copper over in the cathode beaker side is going to be missing all of these sulfate anions that migrated through the salt bridge to the anode beaker side. So these copper cations are going to want somewhere to go. Turns out there's this nifty little copper electrode that has a ton of electrons now. A lot of negative charge. Negatives and positives attract because opposites always attract. So here we have copper positive being attracted to all of these electrons accumulating within the copper electrode. Fancy that. This is the reason why the copper electrode gains mass as the reaction proceeds, because it literally draws the copper cations out of the solution and plates it onto the copper electrode. Now, whenever you're drawing these galvanic cells, make sure you do include the half reactions written below them, respectively, so that you know what reaction is occurring where. In this lesson, we talked about how to write and balance half reactions from a redox reaction, and then use those half reactions to determine the overall big picture of what's going on electrochemically. In order to make a half reaction, the first thing we need to do is assign those oxidation state values to each element and determine if it's a redox reaction even to begin with. If there's no change of charge in at least two elements, it's not redox. Then you need to split up the ionic compounds into ions, into the cation and anion counterparts. Any ions that don't change, like the hydroxide or the sulfate, in the examples throughout the video, are spectators, and we leave them out of the half reactions. They're literally not doing anything for the purpose of our half reaction. The next thing we need to do is show where oxidation occurred or where reduction occurred by drawing where there was a loss of electrons or a gain of electrons, respectively. I like to start by writing out the reduction half because it's easier for me to think about where the electrons are being gained, and we put those electrons on the reactant side since they're gaining. And for oxidation half reactions, the electrons are going to be on the product side because they are being lost. Anytime you encounter a diatomic molecule in these half reactions, make sure that you account for both atoms present in the diatomic molecule on either side of the reaction arrow respectively. This will help you figure out how many electrons were gained or lost. From there, you need to make sure that your electrons from both oxidation and reduction half cancel out, so they need to be the same value. You need to multiply the entire half reaction by whatever number it takes until both of them reach the same electron value. Then you add up all the pieces that are left over for your overall reaction. For a galvanic cell, you're always going to need 2 beakers or 2 separate containers. You're going to want to write the reduction half under one and the oxidation half under the other. Whatever's performing in the redox reaction is the metal that you need inside the beaker. You'll need a solution in there as well, so that anions and cations can go through the salt bridge from one side to the other. You'll need a wire to connect the anode to the cathode metals. Remember that electrons will always travel from anode to cathode. This means that the cathode is going to be the one that gains mass after the reaction is completed. Anode is going to be the one that loses mass as the reaction progresses. The anions will always flow through the salt bridge towards the anode, and the cations will flow towards the cathode. Remember the mnemonic, An ox ate a red cat, to help you easily identify which metal is the anode and which one is the cathode. Chickadee check yourself before you wreck yourself, and make sure that you can write and balance the half reactions for the following redox reaction. Once you've done so, make sure you can also draw the complete galvanic cell setup with all of the applicable labels, including the metals that you used in each beaker, the ions that are generated, the cathode, the anode, the electron flow, the salt bridge, of course, the oxidation half reaction, and the reduction half reaction, written below each beaker respectively. Please give this video a giant quacks up, and when you're out of luck in chemistry, subscribe to the duck. Keep it quacky.
No ducks, no glory.